Okay. Now, from the first two equations of this, consider the first two equations here. We see that from these two equations, we see that phi1, phi2 cos eta, that is phi1 cos eta, phi2 cos eta, and by the first two equations I just showed you, this is R1 phi1 cos eta and R2, sorry, phi2 cos eta and R2, also phi1 cos eta, phi2 cos eta, right? So phi1 cos eta is R1 phi1 phi2 cos eta. That is the first equation here. Okay. For phi2, the same. Phi2 cos eta, that is here. That is precisely the second equation here. Okay. So we have this this equality. Now, this is precisely R1, R2 acting on phi1 cos eta, phi2 cos eta. And this is nothing but R1, R2 composed with phi acting on cos eta. Okay? Phi1 cos eta, phi2 cos eta is precisely phi cos eta. So we can write it in this way. This is true for every cos eta near cos 0, eta 0. We want to prove that our map phi is C1. So we already take an arbitrary point. Cos 0, eta 0 in omega. We take cos 0, eta 0 here in omega. Then we make the above discussion. So this tells us that near this equality tells us that near cos 0, eta 0. Near cos 0, eta 0, phi1, phi2 is R1, R2 composed with phi. This is near cos 0, eta 0. For the map R1, R2, this is near U0, V0. So we can take the inverse of R1, R2, local inverse of R1, R2, composed with the local inverse. We just use the inverse function theorem to see that R1, R2 is locally invertible near U0, V0. That is the image of phi 0, cos 0, eta 0 under phi. Okay, so we take the compose this map with the local inverse of R1, R2. We get our phi is the composition of R1, R2 inverse composed with phi 1, phi 2. So this is C1. Both maps are C1 maps, continuously differentiable. Therefore, their composition is also continuously differentiable near our cos 0, eta 0. Okay. But C0, eta 0 is taken arbitrarily from omega. So this is true that phi is a C1 map. So we conclude that since C0, eta 0 is arbitrary, we see that phi as a map from omega to D is C1. And it is also bijective. We know that it is bijective. Okay. Why it is bijective? Go back to the picture. Given any point in omega, we have exactly one point on the surface. Okay. Then the point on the surface corresponding to the point in omega has exactly one plane emerge under R. Then the definition of phi is precisely mapping the point we taken in omega to the plane image of the point on the surface in D. Such point exists and unique. So this means that our phi is 1, 2 and 1, 2, 1. So it is a bijective map. Okay, so this is a bijective C1 map. But to apply the change of variable formula, we need to prove that phi is a diffeomorphism, or it is a change of a variable. Otherwise, you could not apply the change of a variable formula. So to see the phi is a diffeomorphism, you need to ensure that it's inverse. The inverse already exists because it is bijective. So you need to guarantee that the inverse is also C1. This can be done by computing the Jacobian determinant of this phi. The computation of the Jacobian determinant of phi, if you can show that the Jacobian determinant is not 0, then by the inverse function theorem, we know that phi is a diffeomorphism. Also, the computation of the Jacobian determinant is needed when we apply the change of a variable formula. So we need to do this. So we know that to compute the Jacobian determinant of phi, we know that our phi, I will write here to save space. Our phi is the composition of R under this map phi. This is the relation of our map. Now, based on this relation, we apply the chain rule. This relation means that phi I. Sorry. Okay, I will not. Yes, we take the partial derivative of this by the chain rule. By chain rule. We see that phi C is R U C plus R V C. Okay, this is a consequence of the chain rule. That is, X is phi C eta UV is R. Sorry. UV is phi C eta. So X is also, that is phi C eta is R phi C eta. Therefore the partial derivative of phi which respect to C is the partial derivative of R which respect to its first variable, that is U, multiplied the first variable which respect to C, that is U, U C. Okay, so we have this equality plus the partial derivative of r with respect to its second, that is v, and multiply the partial derivative of v with respect to c. Okay, so maybe I need to write this to make space. I need to write this using this space. uv is phi c eta. Okay, that is phi 1 c eta, phi 2 c eta. So u is phi 1 c eta, v is phi 2 c eta. So the partial derivative of our vector valued phi with respect to c is r with respect to u, and u with respect to c, or you can say phi 1 with respect to c. Okay, so this is the equality, and also we have another similar equality for partial derivative with respect to eta, that is ru u eta plus rv v eta. Okay, so we compute their cross product. So with this we have that we have phi c cross phi eta. Why we compute this? Because in our theorem we have this. Okay, so we need to compute this. So this is ru u c plus rv v c cross ru u eta plus rv v eta. Okay, then by the law of the operation law of the cross product, this is precisely this two terms. The cross product of these two terms is 0. Okay, because the vector part are the same. Ru cross product with Ru is 0. So this is 0. And these two terms give us Ru cross Rv u c v eta. Okay, so we have Ru cross Rv u c v eta. U c v eta comes from here. Okay, and next we compute these two terms. This two term is Rv cross Ru. Rv cross Ru is minus Ru cross Rv, and this have a coefficient u eta v c. Okay, so we have this term. On the other hand, these two terms Rv cross Rv 0. So we only have this. We only have this term. Okay, Ru cross Rv minus u eta v c. So the result is minus u eta v c. The other term is involving cross product of Ru and Rv. They vanish. Only the cross term Ru and Rv, the cross product of Ru and Rv remains. Therefore, this is the result of phi eta phi c. So, taking the norm of this, we obtained the norm of phi c cross phi eta. The norm is the norm of the right hand side. The right hand side here, this is a real number, but this is the vector. So the right hand side is a real number multiplied a vector. The norm of this is the absolute value of the real number multiplied the norm of the vector. So we get the norm of Ru cross Rv, and then the absolute value of the expression. the absolute value of that is precisely uv, the Jacobian determinant of uv with respect to xi eta. This is precisely Ru cross Rv. Then the Jacobian determinant of our map phi. Okay? This Jacobian determinant is precisely the Jacobian determinant of our map phi. So and this need to take absolute value. So we need to take absolute value. So this tells us that J phi is not zero. The Jacobian determinant is not zero at every point. This is not zero because if the Jacobian determinant is zero, then the left-hand side, the norm of the cross product of phi eta and phi xi is zero. But this is not zero because phi is a parametrization of our surface. By the requirement of parametrization, this cross product is always non-zero. So this tells us that J phi is not zero. J phi is not zero, and the phi is a C1 bijective map. According to the inverse function theorem, we know that phi has a C1 inverse. Phi is a bijective map, though, so it has an inverse map. But this inverse map might not be C1. But once we prove that the Jacobian determinant of phi is not zero, we can apply the inverse function theorem to see that phi the inverse of phi is also C1. So in conclusion, we have constructed map phi from omega to d. This is a bijective map, and also C1, and also its inverse is also C1. So this is a diffeomorphism or a change of variable. So we can apply the change of variable formula to conclude our proof. Change of variable formula. Our integral f uv u cross v du dv. I should say that this is evaluated at uv. This equal the integral of omega f. We use the change of variable uv equal phi xi eta. Okay, so the integrand here, the integrand is the multiplication of two terms. The first term is f r uv, but you need to substituting uv by phi eta, xi eta. So f, so this is f r phi xi eta. Then the norm of this, the norm of at the point phi xi eta. Then you need to multiply the Jacobian determinant of uv with respect to xi eta, which absolute value, then d xi d eta. But now what's this? This is our phi xi cross phi eta. Okay, by the previous computation, the last line in this page. So the norm of the cross product of Ru and Rv multiplying the Jacobian determinant of uv with respect to xi eta is precisely the norm of phi xi cross phi eta. We have computed and obtained this result at the end of this page. Okay, so this is omega, and this is f r phi xi eta. Then this is phi xi cross phi eta, and this is evaluated at xi eta. Then d xi d eta. But this is just f because the composition of R and phi is our parametrization phi. So this becomes omega f phi xi eta. Then phi xi cross phi eta at the point xi eta. So this is a function, two variable function of xi eta. Then d xi d eta. So this proves our result. The double integral using the parametrization R is equal to the integral using the new parametrization phi. Okay.